Okay, so let us start lecture 3. Um, so, um, right. So, for lecture 3, I'll review one particular paper um, that that was published in 2013, which is um, kind of a bit it's been a while since it was published, but there were lots of follow-up works based upon this paper, and I guess many of these follow-up papers are a bit more technical, and but this one kind of gives us a nice connection between like online optimization algorithms and reinforcement learning. Okay. So I think if you have implemented some practical like reinforcement learning algorithm, especially for training like post-training large language models, but the thing that we talk about today is a bit different from the practical RL algorithms nowadays. What this is rather like the theory of reinforcement learning, like especially in terms of designing algorithms that have provable guarantees. And also, if you think about like RL algorithms for modern AI systems, they typically work on like discounted MDPs, but what we present today is on like finite horizon MDPs, which is but in the learning theory community, like analyzing algorithms for finite horizon MDPs is rather common. So um yeah, so okay, let me get to the problem formulation. I'll explain the problem setup, which is finite horizon Markov decision processes, which are abbreviated as MDPs. And I'll talk about some online algorithms for learning finite horizon MDPs. So today, I will not talk about offline MDPs, which is more common nowadays in practice, but this is about like online algorithms. Okay, so let's get to the problem setting. So finite horizon MDP is parameterized by these following components, where S is the state space, and I will assume that the number of states is finite, um, and and calligraphic A is the action space, and capital A is the number of actions we take. Also, we do assume that number of actions is finite. And H is the horizon length. I'll get to what it means in a minute. And here, rho is the initial state distribution. So I assume that we take it's okay. You start with some initial state, and then you run your process over capital H steps, and then you get back to the original state. But the initial state, and the initial state is distributed according to this distribution rho. Okay. So here delta S is nothing but the probability simplex over the state space, which is defined by this S-dimensional vector. This is possible because we focus on the finite state case. Okay. Again, you start with some initial distribution according to distribution rho, and then you run your process for H steps, and that will be then that episode is done, and you get back to the initial state and start again this process. And this is the definition of the finite horizon MDP. And uh, and let's say you are at stage H, small h, the P subscript H is the transition probability. So what is it? Let's say you are at state S at stage H, and then you take action A. And now, okay, when you are at state S, you take action A, then you move to the next state S prime for stage H plus one. And here, uh, this is called the transition probability, which is the probability of moving to state S prime, given that your current state is S and your action for state H is A. Okay. Again, you are at state S and you take action A, and the probability of moving to the next state S prime is given by this transition probability kernel. Okay. And you may assume that for distinct stages, you may have distinct transition probability kernels. And here, and L captures the loss function. So I guess in reinforcement learning, maybe reward maximization might be more common, but we will focus on loss minimization just to stick to the convex minimization regime. Okay. So instead of maximizing cumulative reward, we'll focus on minimizing the cumulative loss. Okay. But getting from reward to loss is not too difficult. You can just take the let's say minus of reward, then I guess maximizing reward is equal to minimizing minus of reward, and the minus one times reward can be viewed as loss function. So it's not a difficult issue. So let's say you are at state S and you take action A, then this L subscript S of S comma A is the loss value incurred from taking action A at state S. So this is the finite horizon MDPs. Any question? Okay, so what is online learning for MDPs? So the learning framework proceeds with multiple episodes. So you are, let's say, episode 1. You start with some initial state, and you run your process for H steps, and then you start your process again. Then you get to the second episode. Again, you run your process over H steps, then you are done, and you get back to the original, the only initial state, and you start the third episode, and you do this all the way up to case episode. That's what you do. And we assume that the initial distribution and the transition probabilities are known to the decision maker. But in fact, I talked about follow-up works after this paper. So those follow-up works are tackling the case when these distributions are not known. They are not too difficult. Essentially, those works are built upon this framework and adding the part, but they add the part for learning these unknown distributions. In fact, this second bullet point, for the case when those distributions are not known, can be separately dealt with. So for today, just for simplicity, we'll assume that these distributions are given to the decision maker. Okay. We can deal with unknown distributions. But the main issue that we deal with today is the environment choosing the loss functions in an adversarial fashion. Okay. What it means is that let's say you take a policy for episode K, for some episode, and you run your process, and you only get to observe the loss values only after finishing that episode. Okay? It's not that you know how the loss function behaves. You don't know about the loss function for that episode, but you would have to fix your policy and run your process, and then you get to observe the cumulative loss for that episode. Okay, that is the uncertain part that you have to deal with. Okay. Is there any question about this? This is some. So that's the, I guess, the adversarial part. And also, like the loss functions are not stochastic. Doesn't have to be, they do not have to be stochastic in the sense that they do not have to be coming from the same probability distribution. The environment can adaptively choose the loss functions in response to how the decision maker prepares their policies. So the learning process or the online learning process is about preparing or updating policies in response to the environment adversarially choosing the loss functions. Okay. So the learner chooses a policy pi k before starting episode k. Okay, and it may use non-stationary policies over different time steps, meaning that you may use pi 1k, pi 2k, and they do not have to be the same policy. You can adapt policies for different time steps. Okay? It gives kind of some flexibility for this. And what is a policy? It's like stochastic distribution over the possible actions given as state. So assume that you are at state SH for stage H, okay? And then you're sampling the action AH from this distribution, from this conditional distribution pi H. Okay, again, you are at stage H, and you know that your current state is SH, and then how do you take your action AH? That's given by this policy, which is the distribution, so conditional distribution. Okay, so you get to prepare this policy pi k before starting this episode k, and then run your thing, run your policy, and then after this episode, you observe the loss function. And then based on this, you update your policy for the next episode, and then run your process, observe the loss values, and then update the policy over and over again. Okay. So again, you take the policy, and in response to the policy, the environment chooses some loss function. Okay, in a way that it may kind of deteriorate the performance of your algorithm. And then the learner runs the process and observe this trajectory of state action sequence, as well as the loss values. And then it incurs the cumulative loss for that episode. Okay, again, the important part is that once the decision maker chooses policy pi k, it cannot change in response to the loss function. The learner fixes policy pi k and the environment chooses loss function, and the decision maker incurs this cumulative loss. If you take a look at this SH, AH for a particular episode K, and LHK, LK is the loss function for episode K. Any question? Yeah. That's also possible. That's also fine, but it's not really different from choosing policies for all steps before the episode. Yeah, because so if you have the stationary loss function, which means that if LHK is invariant over different H, then what you are doing is relevant. But LHK can be different for different H's. So if you don't get to observe what LHK, LH plus 1K is, I guess preparing pi H plus 1K right before is really not that different from, okay? Yeah, that's a good question. In fact, for the stochastic setting, when LK, I mean, yeah. So the adversarial setting gives lots of freedom for the environment. So that's nothing that we can do before observing this loss function. So is there any other question? Yeah.
Do we have any kind of prior assumption regarding the problem?
Yes, we will make an assumption that LH is bounded. Like, that's necessary for, getting the performance guarantee. Or for the stochastic setting, some people assume that, it's required that, the distribution of this loss function is, let's say, sub-Gaussian and has some, some light tail, something like this. You have to assume that either the values are bounded or the distribution has some well-behaved structure. Any other question? So, of course, the setting we talk about is rather theoretical. It does not really reflect the real-world problems, but the purpose of it is to look at the abstract and simple setting, and then we design an algorithm that has a provable performance guarantees, and that will provide some insights on about designing algorithms, reinforcement learning algorithms for more complicated problems. This is the purpose of learning theory. Any other question? Okay, great. So the goal is to design on sequence of policies. We update our policies, and in the end, we want to find or compute on optimal policy in some way, and we need to get some get some measure of how good our policy is. And that is, for that purpose, we need this notion of regret. So if you have a policy, the cumulative reward, the cumulative loss is given here. Okay, so and then the expectation is taken with respect to the randomness underlying this random procedure. So your state trajectory and sequence evolves according to your policy pi. So the policy pi itself is a probability or conditional distributions, and p is again a conditional distribution about the next distribution, and rho is the initial distribution. Okay, so SHAH defines a random process, stochastic process according to the policies and the transition corners. And you define this expected cumulative loss. Okay. And the regret is defined as this. So here, so LK pi k is the expected loss for episode K. And this is the loss that I receive under my algorithm. Okay, and then if you sum this up for all episodes, and this is the total cumulative loss for my algorithm. And I compared it against the minimum possible, cumulative loss. I take I take the policy that minimizes this total cumulative loss. Okay, so this is somehow the cumulative loss for a optimal policy, and I compare it with my cumulative loss. Okay, so the goal is to basically minimize this regret function. I design a sequence of policies when I kind of run my algorithm or policies for the different episodes, and in a way that this regret function can be minimized. That is the smaller the regret is, the closer my algorithm is to the optimal policy. Any question? Again, the real difficult part is that, so how do you compute this optimal policy? You need to minimize this the summation. But to minimize the summation, you need to know all these loss functions L1 through L capital K in advance. Okay? If you only get to observe the partial set of these loss functions, you cannot compute this optimal policy. So our algorithm get to observe one loss function at a time, and we update our policy. But when we update our policy and run this algorithm for many episodes, our claim is that we still get to converge to an optimal policy, which requires the all loss functions in advance. That's the interesting part underlying this algorithm. Okay, so yeah. So again, we assume that we only need the assumption that the loss functions are bounded. We'll assume that for today, we'll assume that it's between 0 and 1. But you can deal with any bounded loss functions. As long as the values are bounded, then we can guarantee a small regret.
It is enough to show the regret for about even for the value, and you don't need to determine the exact one.
No. Yeah. Right. So that is the interesting part for interesting result or conclusion for this adversarial losses. So adversarial losses mean it can be anything as long as they are bounded. Okay. So that's yeah. So if you know some structure, let's say if you know that your loss functions are stochastic, meaning that they are coming from the same probability distribution, then you can do a bit more than this. Like you can estimate the distribution, how it behaves, and you can use that information to get a better regret. But even when you don't know what they are, well, you can still get a small regret. That is the nice thing about this online optimization. Okay. But in fact, we talk about this online learning process for reinforcement learning. What I just talked about in terms of minimizing regret, it's not unique to MDPs, but in fact you can you might have heard of this online convex optimization. There you can also define this notion of regret. And for online convex optimizations, you can still define like adversarial loss functions, and you can still kind of argue the similar thing. And what we discussed today is actually motivated from online convex optimization. Any other question? Again, the optimal policy, if you want to compute an optimal policy, you need to know the entire sequence of loss functions in advance, but that's not available. That information is not available to us, but we get an online sequence of loss functions one at a time. We don't get to observe the future, but we still have to make and prepare our policy. And this is the sequence of losses that we get with partial information about the loss functions. But what we'll show is that this value converges to this value in some way, so which is nice. So let me talk about how to design an algorithm that minimizes this regret expression. And so what I'm gonna tell you is that in fact this problem of minimizing the regret can be reformulated as something called online linear optimization. Okay, here, this thing is not convex in pi. Okay, so LK is some function defined this way, and our policy class pi is here. This function doesn't have to be a convex function in terms of our policy pi. But instead of directly working over this policy class pi, we can reformulate this function in terms of something called the occupancy measures. Then we can rewrite this function LK pi as a linear function in the space of occupancy measures. Okay, I'll get to that soon. So if you do that, do this reformulation, then you get an online linear optimization instance. And the idea is that so online linear optimization is a class of online convex optimization. So to solve this thing, we'll apply something called online mirror descent. And using that, we can guarantee a small regret for this online linear optimization class. That is the connection. Any question? Okay. Again, we have finite horizon MDPs with adversarial losses, and we define this regret minimization framework. But the cumulative loss is a non-convex function in terms of the policy. But we're not happy with dealing with non-convexity. So we reformulate the problem further into an online linear optimization. Because we have a linear function, there's some kind of easier handle to deal with these linear functions. Okay, and the final algorithm we will describe is called the online mirror descent. This is the online version of the mirror descent algorithm. How many of you have heard of mirror descent? Okay, not many. Okay. It's okay. Okay, so well, I mean, okay. So what is an occupancy measure? So remember that the policy pi is a conditional distribution. So it's you are given a state S, and it defines the distribution of actions. Okay? So it's a conditional distribution, and occupancy measure is the joint distribution. Okay, so it's like so here you have to take into account the probability of observing the state S. Okay, so this is like it computes the probability of observing the state action pair for step H. Okay, and this notion of occupancy measures is not something new. It's been used for solving, solving Markov decision processes, even for discounted reward and average reward, and even finite horizon MDPs. So this notion of occupancy measures do appear in infinite horizon MDPs as well. This is not something that not something unique for this paper. Anyways, so let's define these occupancy measures. So essentially, it is the probability of being in state S and taking action A at state H. Okay, it's a joint distribution of these two events. Okay, any question? Great. And then why do we care about this occupancy measure? And in fact, it has a nice connection to the policies. Okay, so let me explain some properties of occupancy measures. So for the initial distribution, so here the left-hand side is you compute again if you sum up this distribution, this probability over all actions, then you take out this dependence on action A, and then what you have is the initial distribution for state S, the distribution for initial state S. Okay. So again, QSA1 is the probability of getting this pair SA at stage 1. And then if you take out this dependence on action A, that's the initial state distribution. And here's, you have this transition equation. Okay, so here, if you look at this left-hand side, that is basically, again, this thing, you are fixing your state S prime, and then you are summing up this distribution, the measure for all possible actions. That is essentially the probability of being at state S prime or state H plus 1. Okay, so you are in state S prime at state H plus 1. That's the left-hand side. What is the right-hand side? That is that here again, let's look at this expression. So this thing is a probability of being having state S at action A in stage H, and then if you multiply it by the transition probability, then this is essentially probability of SH is S, AH is A, and SH plus 1 is S prime. Okay. Now you sum up this probability over all possible SA, then that is essentially the probability of having state S prime for stage H plus 1. Okay. So the right-hand side is actually equivalent to the left-hand side. Okay. But the right-hand side has a different expression. So it's like no matter which state action you are in, stage H, you want to it somehow move to state S prime in stage H plus 1, and you sum up all possibilities. And that is equal to the left-hand side, which is just nothing but the probability of having a state S prime at H plus 1. Okay. And it has to be a probability measure. So each one has to be non-negative. And for state H, if you sum up this thing over all SA pairs, then it has to be 1. Okay. Okay. So these are the three basic properties that an occupancy measure satisfies. Okay. And but why do we care about this? Well, if you remember our regret minimization problem, the goal is to compute on optimal policy or find a policy pi k that's close to the optimal policy. Okay. But in fact, we can relate these occupancy measures and policies so that computing on optimal policy can be done by working over the space of occupancy measures. Okay, that's the reason is that here the policy of taking action A at given state S can be expressed as this fraction. Okay. Okay. Remember that this thing is a conditional distribution. So this is equal to probability of S, probability of SA. Essentially, the numerator computes the joint distribution of S and A. And if you look at the denominator, you are summing over all possible actions A prime. So you have only you have the dependence is only on S. So this is basically what you get. Okay, so if you have an occupancy measure, then it's equivalent to having a policy because of this, due to this relation. Okay, so you fix your occupancy measure, then it gives you can infer the corresponding policy from this occupancy measure. So that means that there's a one-to-one correspondence between policies and occupancy measures. We can go from an occupancy measure to policy, and also from policy to occupancy measure if you know the probability, the transition probabilities and the initial state distribution. And furthermore, we were interested in the expected cumulative loss for episode K. Okay, that is equal to this expression. Okay, so what is it? It's the value is the probability of having state S and action A for state H times the corresponding loss function value of SA. If you sum of all these things, that is essentially the expected cumulative loss. Okay. Again, we define this notion of occupancy measure, which is nothing but the joint distribution over states and actions. And if you do that, you can relate it to policies. And at the same time, the expected loss can be expressed in terms in terms of the occupancy measure. Okay. And furthermore, this thing is a linear function in terms of Q. Okay, so if you take Q pi Q as SAH dimensional vector, and each component corresponds to this occupancy, this distribution, joint distribution, then this thing is a linear function. Okay. That's what we have. So we can represent the occupancy measure as a vector and loss function as a vector. Then the expected cumulative loss can be viewed as Q transpose the loss function vector LK. This is linear in Q. Then, using this relation, we can rewrite the regret function as here. I just replaced this LK pi using this expression. I have the summation of linear functions, and I have this summation of the linear function. But the optimal policy can be obtained by minimizing in terms of Q. So my decision variables have become Q instead of pi. Again, just because there's a one-to-one correspondence between policies pi and occupancy measures Q. Okay, and this is essentially this expression. I guess I've talked about many things so far. Is there any question? Right. So let me. I don't know if I have time, but let me recap. So again, LK pi is the cumulative loss for episode K. So you prepare your policy pi K, and this thing is the cumulative loss after running your policy pi K for episode K. And this is a summation of the cumulative losses for your algorithm. And this is the minimum possible cumulative loss, which can be accessible only when all loss functions are available upfront. So this is the way of measuring how close your performance is to optimal possible performance. And the goal is to minimize this regret expression. But the difficult part is that this loss function is non-convex in pi. It's hard to deal with. So instead of working directly over policies pi, we define this notion of occupancy measures Q. Okay. And if you do that, there's a one-to-one correspondence between occupancy measures and policies using this relation. So we can rewrite the loss function in terms of Q. And in fact, this is linear. So that the regret expression that we want to minimize can be written as the linear function minus linear function. And so this is the thing. And this is called online linear optimization. So here, this is one linear function. Okay? And so each time you take a linear function and you decide on your solution, and this thing is the optimal minimum value, possible value of the sum of linear functions when LKs are available to you before, and this thing is the the total sum of linear function values you obtain. And because these LKs are revealed in an online fashion, this problem is called an online linear optimization. Any question? Okay. So we have argued that online MDP became online linear optimization. Now, the question is, how do we solve this online linear optimization framework? And we will use something called the online mirror descent, which is known to deal with this online linear optimization. This is a known framework which is designed to solve an online convex optimization, but we are having an online linear optimization framework, which is an instance of online convex optimization. Okay? So this is a known algorithm, but what we are going to discuss after this point is about analyzing the performance of this known algorithm for the specific setting of our online MDP problems. Okay? So that's this. So so before we talk about online mirror descent, so it's OMD, which stands for online mirror descent. It's on like online version of an algorithm called mirror descent, and mirror descent is on generalization of gradient descent. Okay, if you're not familiar with what it is, so and if you remember gradient descent, it computes gradient at your current solution, and you move along the negative direction of the gradient, and after choosing some step size, and you repeat this procedure, that's gradient descent. And gradient descent is basically x t plus 1 is for the unbounded case, xt minus eta gradient f of xt. This is gradient descent. And this is equivalent to argmin of eta gradient f of xt plus 1 over 2 x minus xt L2 norm squared. I think this is the right expression. So this update is equivalent to finding a minimizer of this sorry, I think it has to be transpose x. Yeah. So if you have this linear function where the coefficient vector is the gradient, and you have the regularization term, which is given by the L2 norm squared. And if you compute the minimizer of this, that's essentially the gradient descent update. Okay, and the idea behind the mirror descent, so how do you generalize this gradient descent? Well, this thing is something called the proximity term. So the idea is that when you choose your next solution, it shouldn't be too far from your current solution xt. And how do you determine how far your next solution would be from your current solution? That is determined by this distance measure. Okay, but this L2 norm squared is one particular distance measure. You can use like different distance functions, and if you take kind of that's how you generalize gradient descent to more general class of algorithms. If you can use different distance measure or proximity term, we still minimize this thing. Okay, that's how you do it. And for mirror descent, the distance measure we use is called the Bregman divergence, and that's for our problem setting, it will be something called the KL divergence, like Kullback-Leibler divergence, which appears, I guess, in many settings. And let me explain that. So you define this some function, and this is called the negative Shannon entropy function, and the corresponding distance measure, which is denoted as this thing, d psi q prime. This measures the gap or distance between q and q prime, okay, which is defined as this. Okay, and this expression, this is the KL divergence. Okay, you may use different classes of mirror maps psi, but if you use the Shannon entropy, then the corresponding Bregman divergence ended up being something called the KL divergence. In fact, here, the summation of Q will be capital H, and summation of Q prime will be capital H. So this term actually disappears, and you just get the KL divergence. But if you just use this definition of the Bregman divergence, you get this expression, and this is called a KL divergence. So as gradient descent, how the algorithm works is that you choose your initial solution, and then you update your next solution based on this mirror descent update. And how do you decide the initialization? So Q tilde one is defined this way. Okay. don't worry too much about like how we set these parameters. Okay, I will just let's give you the pipeline. And Q pi 1, which corresponds to our initial policy for the first step, is you project Q tilde 1 to the set of possible occupancy measures with this based on this distance term. So you're choosing the occupancy measure that has a minimum distance to Q tilde 1 based on this distance measure, and this is called the Bregman projection step. Okay. So when you have the L2 norm squared, that is just the classical notion of projection. When you have this Bregman divergence, it's called a Bregman projection. And when you define Q tilde 1 as this way for the initialization, then for any occupancy measure Q, the distance term is bounded above by h times log of SA. Remember that S is the number of states, A is the number of actions, and H is the length of the horizon. Okay, and the proof is not too difficult. You just again, yeah. Is there any question? Yeah. So Q tilde 1 defines some probability distribution, but we have this condition that if you sum of Q tilde 1 for all actions A, they do not, okay, so sum of Q tilde 1 SAH over OA will be 1 over S, right? But it doesn't have to be equal to the rho of S. So if you assume that rho of S is a uniform distribution, then this will be enough. But if that's not the case, we have to take this Bregman divergence, Bregman projection. That's why. Any other question? Okay. Great. There's a bit more technical step. So we have to estimate the loss function. What do I mean by that? So when you have policy pi k, and when you run this policy for that episode, and you get this trajectory of state and action sequence, and you also get this sequence of loss values. And instead of taking LK, we will use this estimator LHK hat, and the reason is that you get to observe this sequence of values here. Okay, even though you get to observe what LK is later, but the cumulative loss depends only on the state and action you stumble upon. Okay, you don't, in the summation of the loss function value, and the cumulative loss, these are the terms that appear. Okay, so you need to kind of focus on the parts that get to observe, get to be realized. That's why we are defining this estimator, so that the parts that do not appear in the trajectory can be set to 0. And you just focus on the parts that appear. Okay. And you can argue that this LK hat is an unbiased estimator of the original loss function. Okay. There are lots of kind of technical details, but let me skip this part. So here's the online mirror descent update. So again, this thing is the proximity term. So this is the occupancy measure. For episode K. And for the gradient part, we get the L hat K, which is the unbiased estimator for LK. So instead of using LK, we will use LHK, L hat K. Okay, and then you take the minimizer of this thing. Again, this is kind of on generalization of gradient descent step. So you get Q tilde K plus 1. Okay. But the Q tilde K plus 1 doesn't necessarily give you the valid occupancy measure for my MDP. So we need to take the Bregman projection to obtain the next occupancy measure. Okay. So you're projecting Q tilde K plus 1 to the set Q so that you get the occupancy measure for the next episode. Okay. Yeah. Yes. Yeah. What the idea is that so Q here is defined by a bunch of linear constraints, and the the Bregman divergence is defined as the KL divergence. But the important part is that you can easily compute. You can compute the closed form solution for this minimization problem. Okay. Yeah. What's the difference between mirror descent and what? So what is the online part? So the difference is that for mirror descent, you have a fixed function, fixed gradient. So the gradient of the fixed function. But if you look at this thing, the function is different basically. So L hat K. So the online means that, so essentially this Q transpose L hat K is the loss function we observe for episode K. But if you remember the mirror descent algorithm, we fix one convex function and we use this gradient. But this is not a fixed function. We get a different function for each episode. That's the online part. Okay. Any other question? Yeah. No, it's here. So you divide LHK by Q pi K. LK is something that you observe later, but you divide it by the occupancy measure. So you get to observe all values of LH, I mean LK, but this is something that we get for the cumulative loss. So if SA does not appear in the trajectory, then this term doesn't appear in the cumulative loss, but you still get to observe what it is, but it just you don't get it in the cumulative loss value. Right, so we are almost done. So this is basically the algorithm. So we prepare we have our current velocity pi k, and we run this process for that episode. We get to observe the trajectory of set action sequence and also the corresponding loss values. Then we use that to get an estimator of the loss function. And then we take on online real descent update to get the next velocity. And you repeat this process. That's the algorithm. Yeah. Yeah, I think so if you use LK, you cannot get a bounded regret in some ways. That's a good question. Uh, 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 yeah, I think it's just uh, okay. So right. So let me get back to this thing. I think getting back to your question. So right. So this thing um so this is the banded feedback setting. So it's not that we see all values. We only observe these values. Okay. So my answer to your question was wrong. So it's not that we get to observe all possible loss values. So we only get to observe the values for the loss function on this trajectory. Okay. So the question was that why do we use LK? Well, we don't have this full stack of LK, but we only have these things. Okay. Right. So we don't have the other loss values for the ones that we don't get to observe. So well, we can take this estimator, even though LK is not known. But if you use this thing, we still have on, so LK, the entire vector is not known. But if you construct this estimator, we get on, we know that its in expectation is equal to the loss function. Okay. I think then that's any other question? Yeah.
So we partially observe the result of action A. Then we reconstruct the estimation of this, and then we can compute the estimation of all. We partially observe the.
Well, I mean, you have the probability of choosing your action A. Right, so right, but you have to still sample your action according to that distribution, which is AH. And then the loss value you observe is just on LA. Right.
Other or other things, not
No, because you don't get to see this value. Well, yeah. Well, this is the random variable you have. You don't get to see the expectation. Okay, in expectation, we know that this thing is given to you, but what we have in our hand is this value, which is a random variable. But we don't know the expectation. It's especially when when SA doesn't appear in the trajectory, its value will be 0. Okay, with some probability it is non-zero, but in other case it will be 0. But if you take the compute the expectation, that will be the actual loss function LK. Okay. Sure.
because
Okay.
But why do we deal with this frequency that I don't want to when we use I just curious about when we use theta regret and frequency.
Well, frequentist regret will imply Bayesian regret, but if the converse is not true. Obtaining the frequentist regret is stronger than getting a Bayesian regret.
The other way, this was not simple or easy to show the convergence of Bayesian. But why is it not enough to show the Bayesian?
You mean like well, first of all, frequentist regret again, it's a stronger result. It's something harder to obtain, and well, Bayesian regret, it's on the the assumption, the Bayesian assumption on like your model. I mean, it really depends on the setting you have. I guess you need to assume. I mean, for Bayesian regret to be meaningful, you need to really kind of it really relies on this kind of prior assumption on like how your prior distribution behaves in term and also posterior distribution behaves, and um, well, I mean, it's used to kind of model on certain cases, but I'm not so sure if it's sufficient. Yeah, I mean, even for bandits, I guess you can derive like Bayesian regret, but I guess obtaining frequentist regret, uh, uh, I mean, does this answer your question? Okay. For online optimization, yeah, like when you have like adversarial losses, or when you assume, okay, right. So Bayesian regret for this setting, you cannot expect to get a Bayesian regret because the losses can be arbitrary. It doesn't necessarily follow that Bayesian assumption. But if you have a stochastic bandits, you may get to, you may attempt to get the Bayesian regret. But this is adversarial losses. Okay. 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 So this is the algorithm. Okay. And because we have used the online mirror descent update, we can use this lemma. Okay. And then you get this regret bound. Okay. If you see this expression, H can be viewed as constant, and SA can be viewed as constant. But if you just focus on the dependence on K, the regret is a sublinear function in terms of K. So what it means is that if you divide the regret bound by K, 1 over K times regret goes to 0 as K goes to infinity. Okay, so what it means is that, I guess, if you run your algorithm for sufficiently many episodes, then it will converge to, I guess, the cumulative regret kind of gets close to the cumulative regret under an optimal policy. So let me skip the proof, but I will share my lecture notes with you. And for here, let me just, sorry about getting a bit over. So when P and rho are not known, there's an algorithm with regret bounded above by H 3/2 square root of S times A K. As you get an additional dependence on the number of states and additional dependence on the H, and lower bound is omega of H 3/2 square root of S A K. So if you are just happy with the dependence on the number of episodes, then even when the transition probability and initial distribution are not known, you can still get the same square root K regret upper bound. Let me stop here, and I guess we'll resume at 3:30.